I'm Ian, I'm from Johns Hopkins, and this is a talk on how to add forward security to asynchronous messaging. So think things like SMS or email, where the party you're communicating with isn't actually online to receive the message immediately. Right? So forward security is, of course, motivated by the, can someone get the next slide? This is really not working. The question of what happens when if your keys are compromised, and this is not a theoretical question. Next, please. It can happen because you get exploited. It can happen because you end up with some determined attackers going after you, or it can just happen because you screw up and do something stupid, for those of you who remember this talk from the Usenix or crypto rump sessions a couple of years ago. So when that happens, you would really like to have forward security. Because if you have forward security, then an attacker who gets your keys can't use them to decrypt old messages. On the other hand, if you don't have forward security and you start contemplating this scenario, you're going to start empathizing with the duck from the previous slide, because you're going to realize that now that the attacker has your keys, all they have to do is find some copy of your message encrypted that's sitting somewhere on the internet. And that might be on a mail server, it might be on a large data center in Utah somewhere, it doesn't really matter, they'll probably find it. And so then you're going to realize that effectively, every time you hit delete on your email or on your messaging system, you didn't really delete it, because you deleted the copy you had, but since you kept the key around, and since the attacker kept the encrypted copy around that they got coming through some fiber optic cable somewhere, you've got a problem. So luckily, we know how to fix this and do forward security for synchronous protocols. It's very simple. You do an authenticated ephemeral key exchange. You get a key that you use for a little while, then you throw it away when you're done. And this is actually used for messaging protocols via OTR and also via the Oxalotl ratchet and TextSecure, and then therefore WhatsApp, which sort of uses TextSecure. And these provide a very good standard, sort of the gold standard for forward security, because not just do you have a key that you're using for the 20 minutes you're having a chat, but you actually end up doing symmetric ratcheting to get every single message sort of has its own key that you throw away immediately afterwards. So the moment you read a message, it's effectively gone. And so this is nice. We'd really like to have this kind of stuff, and there's a lot of interest in this, hence the SOK and secure messaging. Unfortunately, this model doesn't really work for changing slides. And then it does work. It doesn't work for most electronic communication, because a lot of them are asynchronous. You end up with things like email or SMS messages, right, where the other party simply isn't online. Even for chat protocols, right, these things end up wanting to do offline message delivery, right? Like this is what Skype, iMessage, WhatsApp, all of these things do. And so you can't use the existing techniques we have. And then you just have this gap where you can't get security for a feature people really want, right? And this is a big problem. So how do you fix this? Well, the current solution is you fake it. Right? You have, instead of having Alice and Bob both be online, you have a server that Bob pre-provisions with keys, and then when Alice wants to send a message to Bob, she negotiates a key with the server on Bob's behalf. Now, this server isn't trusted in the sense of if it fails, it can read your messages, but if it fails or is malicious, it can mean you don't have forward security. So not the best idea. It also needs to store all this key material, which is a pretty large scaling issue, especially if you're trying to deploy this for, say, WhatsApp, which they are trying to deploy. You have like 800 million users. It's also difficult to add to old protocols. It's not quite clear how you'd stick this into email or some other stuff. So ideally, and this is the problem we're trying to solve, you would like to get rid of the server and get forward security for asynchronous messaging without resorting to these kind of tricks. So what do you do? Well, a naive solution would be to just have one public key, private public key pair per time interval. So think like the first day of the month, the second day of the month, et cetera. And so encryption on this is simple. You pick the correct key, you send the message. Decryption looks the same. And the only thing that really changes is when that day is over, or whatever that time interval is, you delete the current key. This gets you forward security because once you get compromised, you don't have the material to decrypt it anyway, so you're good. This has a major problem. It has way too many keys. So first, you can get rid of the public keys. Next slide. You can get rid of the public keys by using a thing called identity-based encryption. And so in identity-based encryption, you have one public key, but you can actually encrypt under distinct identities, like google.com, example.com, et cetera. And those each have a separate secret key to decrypt. So what you do is instead of identities, you use time intervals. So the first day of the month, the second day of the month, et cetera, et cetera. And then you generate all the secret keys for that in advance. So this gets rid of the public key problem, but it still has way too many secret keys because you have to have one per each time interval. So this brings us to sort of the more elegant solution, which is a thing called forward secure public key encryption. This is due to Canetti, Levy, and Katz from 2003. They got short public keys via that same trick. They got logarithm-sized secret keys, and the way they did this was by using a thing called hierarchical identity-based encryption. So instead of just having identities, you have hierarchies of them, where like the key for, say, google.com can derive subkeys for like mail.google.com and things like that. And so the way you do this is, for forward security, is you map time intervals to this tree of keys, right? The root of the tree is the first time interval, the child of that is the second, the child of that is the third. This is just a pre-order traversal of a binary tree. So at time 1, you are holding just the key for time interval 1. You can decrypt messages. When that changes, you derive new keys and delete the existing key. And you can keep doing this. And you end up with a scheme that's actually quite efficient, and you never end up holding a linear number of keys that's only logarithmic. So this is a really nice solution. In theory, it gives you all of the things we'd want. When, and only when, everyone knows exactly what time it is, and your messages are showing up exactly when you expect. The problem is, we don't live in that world. We live in a world where things go wrong, such as this clicker, and you get latency. Emails can maybe take days in the pessimal case, I think. I haven't actually been able to find data on this, but I swear I've seen things where that must have happened, or people told me that happened to them. SMS messages can take more than an hour to deliver in some cases. Mixed networks, of course, add latency intentionally, so does gray listing for spam prevention. And then you have the whole entire problem of clock skew and misconfiguration. I guarantee you, if you deploy one of these protocols, you end up with someone sending you a message for the time interval for January 1st, 1970. Maybe you don't have to deal with that specific one. That's too far off, but you will get problems. So let's assume for a second that you can just assume away how many messages you're going to get and think, I'll just get one message per time interval. Right? Just somehow get that. And then you could do something interesting. You could delete keys only when you get messages. Right? And so then you could get, you could skip time interval 1. You didn't get anything for that. You did get one from time interval 2 and time interval 3. And so you delete those. But you're still safe. You've still got forward security because you deleted the keys that could decrypt those messages. Well, you did, but the problem is you didn't delete the keys that you could derive to get those messages. And so this solution doesn't entirely work, right? It's a nice idea, but you can't quite get this thing to work the way you want. And so we sort of need a completely different technique to apply. Because really what we've been doing this entire time was we're trying to do this synchronously. Right? And so we gave up on that because we don't have synchronicity. So now we're sort of trying to just like take out little pieces of our key space as we go. But this technique isn't really suited to do that. So let's sort of start over from scratch and let's skip that slide. Try something different. So what do you do? Well, suppose that you just had messages which have a unique random tag, and that every time you get a message, you can simply revoke the ability to decrypt on only that tag. This would be nice. This would get you the sort of fine-grained forward security you want, because the moment you get a message, you update your key material, and you have no problem. You're now forward secure. And it would solve a lot of these synchronicity issues because the order wouldn't matter. Right? It doesn't care which order these messages get in because you've still just updated the key. And so we call this puncturable encryption because you effectively just end up poking very precise holes in your secret key. And so the question is, how do you build this? Well, there is an interesting thing that you can get negations for an attribute-based encryption. And so remember, attribute-based encryption has this notion of you have access policies for ciphertexts that have attributes on them. And it turns out you can have policies that say you can do anything if you meet some preconditions and not X, or like not your message is top secret. right? And so this is a very nice starting point, because effectively, we need this exact technique. We want to be able to take a message, a key that we have, and make it say, and not this specific message, where that is a random tag that we put in the thing, right? So that would be really nice, and this would almost get us this. But the problem is that we can't take this scheme and add negations. So we can't take a key that says and not message 5 and add it to say and not message 5 and not message 42, right? These are both random tags on the messages. And because you can't do that, we can't quite get this to work. Thankfully, though, you can update this scheme so that you can actually do that, and you have to do a few tweaks. The first thing you have to do is you have to remove all of the notion of negations, of everything but negations. You can't have other policies. And the second thing you have to do is store a special negated key that's not actually used. We call this the null tag, right? You will never tag a message with this, but you have to have it in your crypto system. And so what happens is every time you get a message, you take the existing negated key that you have, and you split the secret in that into a negation for the message you got and a new version of this negated null tag, right? And then when you get another message, right, you just repeat this process. And you keep updating the null tag, and you add these new negations. So this works quite nicely, but it has a pretty obvious limitation to it, which is that this thing grows linearly, right? If maybe you can get this to work for a minute or an hour, but sooner or later, you're going to have received enough messages that you have negated this thing too many times, right? And it will still work, but since the key grows linearly as you do this, and your decryption time grows linear as you do this, it's just going to become cost prohibitive. So effectively, we'd have to have one of these keys every day or every month or something, and that sort of gets us back to that straw man solution of have one key per day. So you want to actually combine the two approaches, right? You'd like to have punctures only per every individual time interval. And each time you go to a new interval, you actually reset on the number of punctures. So it turns out you can do this. You basically have to combine the two schemes. It's a little more complicated than just encrypt under both, because if you encrypt under both, if one of them is compromised, you still lose. You actually have to re-randomize the keys together every time you do this in a very particular way. But the gist of it is you can get it, and it's actually fairly cheap to combine them. And so then what you get is this ability, which is what we always wanted, to deal with late messages, because we can just keep all of the keys around. But we can update each one of those keys so that it can't get whatever messages you got in that specific interval. So this is nice, and this isn't actually just a theoretical thing. We actually built this. It's about 4K lines of C++. It has separate implementations for the BBG HYBE scheme, the Puncturable PKE scheme, and the combined one. So you can use these individually if they're of interest to you, or you can use the combined one. It uses BN256 curves in the relic pairing library, which, as far as I know, is sort of the fastest thing you can use that's easily available. And actually, that last point is a lie. The code is actually up online now. And as far as I know, and I may be shooting myself in the foot here, you should be able to download it, install the dependencies, and it should compile and pass tests on all of your systems unless you're running Windows. Well, we'll see about that, I guess. So we built this. How does it perform? Well, so the first question, and this is sort of an interesting thing that we had to deal with, is how do you even test this, right? I could give you raw numbers for the primitives, like how long it takes to decrypt if a message is unpunctured or things like that, but those are pretty useless, right? You want to know how long it takes to decrypt after you've gotten like 50 messages or something, but you don't know particularly what the distribution of messages are, so we've got to make some simplifying assumptions. So the first thing we did is we assumed that your messages are distributed with a Poisson process, and you get them at 1 per x, whatever x is, and we varied that. So once you do that decision, the question is then, how big do you make the intervals, right? I've been saying once every day. You could do once every second. If you don't talk to very many people and don't get very many messages, you could do once every month. It varies. And it also really varies depending on what kind of messaging system you're using, right? You'll get more messages on a chat protocol than on email per second, I guess. And so we tested a bunch of different scenarios. And it turns out, and this is sort of a funny result to me, that the optimal choice you pick is you want to pick your interval sizes so that you expect to get 1 message per interval. And why is this funny? Well, it's funny because you think about the entire line of slides I just went through of here's the existing tree-based stuff, here's an adaptation to it, and then here's the puncturable encryption scheme, which is what we actually started out on a whiteboard that motivated this paper. If you're only getting expected one message per interval, you don't ever actually use the puncturable encryption stuff, really. But you do still need it, right? Because you expect to get one message per interval. But if you get unlucky, right, if you guessed wrong, and you will occasionally have guessed wrong, you then have this to fall back on, right? And so when you assume one message per interval, how well does this thing perform? Well, so the average performance is it takes expected 20 milliseconds to decrypt with 99% probability, again, because you have a probabilistic distribution on the messages. And total time to handle a message is less than 100 milliseconds. On a phone, it's a little worse. It's 55 milliseconds to decrypt with 99% probability. It's less than 500 milliseconds. And there are some optimizations you can do to this. In particular, this data was for when you get a message, you try to derive the tree-based key for that time interval immediately, if you already haven't. And you could batch those up and do them beforehand, and that would save you some time and power and having to wake the phone up. So you'd probably want to do that in practice. The ciphertexts are actually pretty small. They're about 0.5 kilobytes for just encrypting, say, a symmetric key that you use to actually encrypt the message. But most importantly, you only need to use this scheme for the first message that you're sending to someone you don't know. You don't need to use this for every single message. You're only going to use it when you talk to someone you've just met and you haven't exchanged a key before, because you use this to bootstrap a symmetric key that you just use between you and them, and then you can use something like the axolotl ratchet to actually get fine-grained security. So this actually, I think, scales pretty well for the use case of introduction to each person once. It actually probably scales well enough to do real message throughputs, but I mean, there's sort of a distinction between what I think is practical in terms of times and what people who make software that has to run on real mobile phones and get comments about it's killing their battery life is practical. But I think it's definitely practical for that. And so in conclusion, latency tolerance is actually quite important for forward security, and it's sort of been an ignored property in terms of the theoretical work. We want and really need fine-grained forward security, and we actually got both of these by doing this. And so with that, I'll take questions.
Okay, are there any questions?
In some identity-based encryption schemes, you have to rely on some form of key escrow.
Sorry, say that again?
In some forms of identity-based encryption schemes, you have to rely on some form of key escrow.
You don't for this one, as far as I know.
OK, great, thanks.
Hi, Ian.
So this will give you forward secrecy as long as you actually received the message.
So I have a slide explaining that, and I actually should have put your name on it, because I was guessing you were going to ask this. Shouldn't have put this so far through the thing. So yes, it's a very good point. So there is an issue which you're only getting messages in the puncturable scheme. You only update your key when you delete messages, when you get the messages, rather. So if there's an attacker who drops your messages and then later comes and gets your key, they'd be able to decrypt them. So the first point is, for the combined scheme, there's still this time counter moving around. Sorry, there actually isn't. For the combined scheme, however, or this one, you can have a window, and after that window expires, you can just delete the keys no matter what happened. And so that window might be like 12 or 24 hours. It might be some complex notion of when the last time we saw you online was. This is what TextSecure also ends up having to do. The second point, though, and I mean, it's a valid point to ask the question, is I'm not entirely sure this is something you have to worry about, because I'm a little confused of who the attacker is who can mess with your network traffic. You can clearly do that. Can compromise your system. You can clearly do that. But is going to do that and then steal your key. Because if you're dealing with like the NSA, they'll break into your thing, they'll put a bug on it, and they probably would have done it before you sent the message in the first place. So it is a valid point. We do protect against it.
Well, you can imagine an attacker that's waiting for you to enter country X.
Yes.
right? And a message is coming to you, they intercept your network connection, and
Yes.
then you land at JFK, I mean at country X, and
Yes, okay,
they
all right.
dump your key.
That actually answers a good point, then yes. But anyway, we do deal with that, but you do have to pick there's a tension between how likely that attack's gonna happen and how long you wanna deal with late messages normally. So if you're Ed Snowden, you probably wanna set that to be like 5 minutes. If you are me and you don't really care that much, 24 hours is probably fine. But yeah, you do need to deal with that, and you can. Incidentally, you can actually deal with it in just the puncturable scheme, but you have to have 2 tags instead of 1, and one of them has to be the time period. And then like when it's up, you just puncture no matter what on that time period.
Thank you.
Great. Let's thank Ian and everybody from the Crypto Protocol.